Good morning, everyone. I am Sahiti. Today, our group is presenting human activity recognition using feature engineering on Stanford 40 dataset and HAR baseline study. Our team includes Shravani, who worked on the image-based feature engineering pipeline, Navya, who handled image pre-processing and feature extraction, and Jaya, who worked on HR autoencoder. I am Sahiti, and I focused on feature selection part. The motivation for our work comes from a major issue in human activity recognition: high accuracy can hide serious bias. So in the reference paper, elderly users achieved only a 34% of F1 score, while young users reached 100% on the exact same system. Yet, the overall accuracy still looked good at around 85%. So this 194% gap is unacceptable, especially for applications like hospital fall detection, smart home elderly care is and rehabilitation monitoring. So where fairness directly affects safety. So this leads us to a research question, that is, can ethical feature engineering principles from sensor-based HR be extended to the image-based action recognition while maintaining fairness across demographic groups? So this matters because both sensor data and image data are used in high-stakes environment such as wearables, CCTV systems, and smart homes. Now my teammate Jaya will continue.
Coming to the reference paper and ethical framework, our work is based on the paper Ethical Feature Engineering for Human Activity Recognition. The paper talks about the three simple ethical ideas: the outcome-based ethic, the fair distribution, and the transparency. The outcome-based ethics should be the focus on final result. The model should be equal for all the well-known users. The fair distribution, we should get a gap between the best performing user and the worst performing user, not to just increase an average of accuracy. Transparency uses the feature and clear, understandable, not for the black box features. From these three ideas, we have followed three principles like equal performance, avoid hidden bias, easy to audit. Coming to HR database, the baseline we have used 33 people, 6 activities, accelerometer, gyroscope sensor. Using the sliding windows, the datasets having almost 4,000 samples. Here the feature extraction. Here the 120 time-based features like mean, RMS, skewness, 54 feature-based features or FTTNSG, dominant frequencies, and 12 combined features, that is both sensor together. From baseline, we have tested 3 models for using loss of validation. XC-Boost give the highest frequency for 96% to random forest, SVM to 95%. Comes the feature selection. Feature selection.
Yep. Now coming to feature selection, here we are using 5 different methods, which are variance filtering and correlation filtering, mutual information, recursive feature elimination, and model-based selection. Now, comparing the selection models, once we build the model, we are getting the following accuracies and FN scores. Now, coming to optimal features and save, here are the optimal features of FN scores, and then recall. Now, my teammate will continue.
Yeah. Coming to the per user normalization. Here, the graph shows that the histogram. Once again. Here the graph shows the left side of histogram. The histogram shows the individual of very high frequency, close to 0.9 to 1.0, which looks good. And some of the same time, the few users has lower score and down scoring of 0.34. The green line shows the represents average of FN score, and the red line shows the median. And here the right side, the box plot shows the upper side of 0.91, 0.9 plus F1 range. That's so the model has accurate but not equalability. Coming to global normalization, per user normalization, different users have the blue line shows the what happens when the normalized everyone data is together, and the orange line shows the what happens in the normalized each user separately. Here we can see that some of the users like user 16 and user 28, or the two lines are different. This means the global normalization and distorts their data because their sensors or ranges very different from others. But per user normalization, the orange fits a naturally pattern better. This reduces the bias and gives more fair result across the users. Coming to autoencoders. The graph shows that autoencoders learned more over 100 epochs. Like the blue line shows the training loss, the orange line shows the validation loss. The both lines drop quickly, begin slowly, and slow out. And the model is learning to reconstruct the data better over time. By end, both the loss and reaches around 0.05 MSE. They stay very closer to each other. The main important point is to train and validation of the curves almost overlapping. This shows it is no overfitting, and autoencoder is generalizing well. So autoencoder is stable, learn clear patterns suitable for diagnosing. Next will be continued by my friend.
Okay, coming to the image data set, now let's extend this fairness principle to the image-based action recognition. So the data set which we use is standard for 40 action with 953 images, and which contain 40 actions, including the brushing teeth, playing guitar, waving hands, from 180 to 300 images per class. So the challenges we faced are the cluttered background occlusion, which is nothing but objects blocking people, poses version, some actions with same actions like with different angles, why it is harder than the sensor HR. In the sensor HR, the clean 1D time series, and the image is high pixel, which is 150K pixel. So the pixel varies like skin tone, clothing, body shape. So basically our goal is to build a fair action recognition that does not rely on appearance proxies. Coming to the code. So this is the data set which is loaded with HAR activities from the standard FR40. These are the sample images. You can see the walking, running, jumping, and climbing. Coming to the feature extraction part, first feature is a color feature. This feature set extract low-level coloring characteristics from the standard HGR images. Each image is represented by a 1 to 3 dimensions. These are the three components: HGR histogram, statistics, and HSV another statistics. Let's go into the visualization part. This is the original image, red, green, and blue. We can see the dominant colors and the RGB histogram, like with the channel statistics. The second feature, which is the text feature. So this is a feature that captures the surface structure and the structural pattern in the human activity. So basically it captures the details of the object shapes and edges oriented. These are the three more components. Coming to its visualization. This is the original normalized and the grayscale. This is the HOG visualization and the histogram, LBP and its histogram. And the third extraction is the edge and shape feature. So these are the four features. But one is the canny edge feature, Sobel gradient feature, contour based feature, and the Lapakel feature. So coming to its visualization. Yeah, this is the original image, grayscale. You can see for Sobel X horizontal and Y, every shape and edge are very clear, demonstrated in this visualization. And yeah, coming to the deep CNN feature, basically it's like a pre-trained model which is used for which is mobile NET v2. Coming to its visualization. Yeah, these are the contours and the layer channels. We can see more clear features were extracted in this feature. And next, my friend is going to continue.
Coming to the feature selection for the image part, so we are removing the noisy and irrelevant and redundant features which affect the accuracy. We don't want them. So these are some of the methods that we use for the feature selection, like variance threshold, ANOVA F-test, recursive feature elimination, and the tree-based importance. So we have used this feature selection for our model building. And these are the features extracted and removed. These are methods used. So when we have visualized that, we could see like when we use the variance, this is the feature variance distribution and ANOVA F-test, and this is RFE, and this is the comparison method for the feature selection for the features removed using that method. When we model that using before the feature engineering, we got the accuracy of 92% to 92% for the logistic, SG, and random forest. But when we have model trained our feature engineering using all the feature extraction and feature selection methods, our accuracy has been decreased to 87%, which means that like not always including every feature in our model training increases our accuracy. Next, we have doing the application study. This is a study which says that like when you use the features, how it will influence the model accuracy or not. So when including and excluding of features, so we are just making a study like how it depends the model accuracy. So here, when you see when you're using only color features, texture features, and edge features, the accuracy was low for the logistic, XG, and random forest. But when you have removed that, we got a very good accuracy. And when you compare with the CNN model, and we got a very good accuracy of 90% because we have used a pre-trained model. So it doesn't require our existing features to train our model. That is why we got a similar accuracy with and without CNN. Coming to the per class normalization, before in the baseline HAR, we have used the per user normalization, but here we are using per class because we are classified based on the activities. So when we have compared the results with and without normalization, we have generally done the normalization using the standard set score and everything. So when we have done that, the accuracy was good for the normalization and compared to the without normalization. This is a F1 score. This is a recall precision. And next is coming to the autoencoders. Autoencoders is a process when we remove some of the features and we remodel the training, then we see how the accuracy is improved or decreased. So when you see like when you use the original handcraft features, the accuracy was 40%, but when you used only less handcraft features, the accuracy was increased to 52%. So it means like less features in the handcraft increase the performance. And when you compare to the combined features, when you have less combined features, the accuracy was dropped. So we have a mixed reactions here. So, but in the CNN, the results were same because it's a pre-trained model. These are the comparison configuration of each F1 scores. And next, coming to the conclusion and future work, our ethical engineering, feature engineering that we have done as extended from like sensors to image, we have implemented successfully. And the per class normalization is very effective. And we have made the 3D-based selection for which improve the good accuracy. And what the lessons learned is like we have from the sensor HAR with the time dominant or dominant features, and for image we have the CNN, which is powerful, but handcraft features which improves the audibility. And future work, we can extend our temporal features using the LSTM and transformer, and we can collect the demographic metadata like gender and age or disability. And also we can also test on different kinetic data sets, and also we can partner with the hospital for the more real-time data to get the more LLT monitoring data set for this project. Thank you.